Someone asked me what the ninth letter of the alphabet was. It was a complete guess, but I was right. What's the difference between Boba Fett and a time machine operated by Marty McFly? One's a Mandalorian and the other's a Mand-DeLorean. What do you call a tiny mother? A mini-mum. Hi, my name's Tony, and this class presentation is on Chapter 11, Cerebral Asymmetry, and because they're so similar, Chapter 12, Variations in Cerebral Asymmetry. I'd like to start off by letting you know that this entire video script and all images are available through the Google Docs link provided, so just sit back and enjoy. Feel free to make a copy so that you can add your own notes as we go. A little bit about myself. We each have our own motives for learning about the brain. I've really enjoyed learning these things with you guys, as sharing these things with family and friends often just gets me weird looks or blank stares. My personal reason and passion for learning more about the brain is extremely aspirational, I realize, but I'd like to discover the connection between our physical and spiritual brains. I'd love to hear more about what your motivations are for learning more about the brain. Please feel free to make a comment or just respond to emails or just reach out. I genuinely am interested in that. A little more about my interest. I believe that God designed and made everything we perceive, that there is symbolism in it all. The tree, for example, with its roots and branches, the sun, moon, and stars. I similarly find potential for symbolism within each of us, God's greatest creations that we're aware of. If the great designer of us all can and has placed symbolism in our greater learning and understanding in perpetual things like nature, our solar system, our galaxy, and even the universe, then why not place symbolism in other perpetuating things like us? I see the potential for symbolism in cerebral lateralization. We don't really know why opposing sides of our brains control opposite sides of our bodies. We'll dive into this a little bit more later. So chapter 11, it's pages 309 to 345. And we'll start out with, at the beginning of the chapter, with the story. MS, a 25-year-old mother of two, had a lifetime history of epilepsy. Her seizures were well controlled by medication until after her second child was born. From that time, she endured about one uncontrolled seizure a month on average. Neurological examination revealed that the source of her seizures was a long-standing cyst in her left temporal lobe. MS agreed to neurosurgery to remove the cyst and the surrounding abnormal brain tissue. The accompanying photograph, a transparent representation of an intact cerebral cortex, highlights the major left hemisphere language areas with Broca's area in green and the Wernicke's area in blue. The yellow area is the corpus callosum, which connects the two hemispheres. Initially, MS's postoperative course was uneventful, and her seizures appeared to be cured. Unexpectedly, she developed an infection that proved resistant to antibiotics. Within a few days, MS suffered extensive damage to her left hemisphere. The illness left her unable to either produce or understand language, a condition known as global aphasia. For weeks, the only words that she was able to say were, "I love you," and she said them to everyone she knew well. In spite of her severe language problems, her ability to enjoy music was unimpaired. MS could sing versions of songs that she had known before the surgery. Thus, although she could not use or understand words to talk or read, she could use words in music and could tell immediately if the words in songs were wrong. Learning the words to new songs proved to be very difficult, however, though she was able to learn new tunes and hum along. That outlines a little bit about what we're going to be discussing in chapter 11. And the gist of what we're going to be studying is these two main points. The majority of left hemispheres controls language and movement on the right side of the body, and the right hemisphere controls visual spatial information and synthesizes nonverbal information, including music and facial expression, as well as controlling the left side of the body. We'll dive a little deeper as we go along. Much of the information given in this video will be generalized to the statistical majority, because the study of the brain and its lateralizations are still relatively new. There are typical anomalies and general differences, for example, left and right-handedness and male and female genders. We will dive into these differences a little later, but for now, here are some general points from the book. For the most part, left and right hemispheres are symmetrical. There seem to be redundancies in place if a loss occurs in one hemisphere. The other can start to pick up the slack. Our brains are malleable, particularly in our youth. Cerebral asymmetry is more common in right-handed males than women or left-handers. On average, in 65 of the 100 brains studied by Gershwind and Levitsky, the planum temporale was in the left hemisphere was nearly 1 centimeter longer than that in the right hemisphere, which has been generally associated with right-handedness. Some other notable differences are the right hemisphere is slightly larger and heavier than the left, but the left contains more gray matter relative to the white matter. The temporal lobes are different. The asymmetry in the cortex of the temporal lobes correspond to the asymmetry in the thalamus. The slope of the lateral fissure is steeper on the right, and the left side Broca's area is larger and is organized differently than on the right. The left side affects grammar and language, and the right side possibly influences tone of voice. We're still not sure. There is a different distribution of neurotransmitters left to right. The right hemisphere extends farther forward, and the left hemisphere extends farther back. The occipital horns of the lateral ventricles are 5 times as likely to be longer on the right as on the left. These asymmetries presumably correspond to some gross difference in cerebral organization that has yet to be identified. One of the presumed reasons for these differences are gender and handedness. It is thus tempting to speculate that the asymmetries evolved to subserve language. Asymmetries are present in preterm infants, which seems to support their proposition that language is innate to humans. And with these things in mind, it would appear that we are designed for linguistic and social behavior. In this image, the biggest differences in cerebral lateralization are in red, and the least are in blue. Most common in blue. And these are the basic references for the information we've gone over so far. Another difference assumed to be genetic is handedness, which to date has no known basis, which makes it all the more fun to speculate. Here are some examples from the book that describe what can happen when parts of the temporal lobe are removed. There's a significant difference in IQ when those things happen. There have been some interesting tests done on seizure victims who have had their 2 halves separated, a procedure called commiserectomy to separate the corpus callosum. And this was first performed in the 1940s by William van Wagenen, an American neurosurgeon, which makes me wonder if the Germans weren't the only ones performing human experiments. To best describe this, I'll read straight from the book. Patient NG, a California housewife, sits in front of a screen with a small black dot in the center. She is asked to look directly at the dot. When the experimenter is sure she is doing so, a picture of a cup is flashed briefly to the right of the dot. NG reports that she has seen a cup. Again, she is asked to fix her gaze on the dot. This time, a picture of a spoon is flashed to the left of the dot. She is asked what she saw. She replies, "No, nothing." She is then asked to reach under the screen with her left hand and to select by touch only from several items the one object that is the same as she's just seen. Her left hand manipulates each object and then holds up the spoon. When asked what she is holding, she says, "Pencil." When the left hemisphere, which can speak, sees the spoon in the right visual field, the subject responds correctly. When the right hemisphere, which cannot speak, sees the spoon in the left visual field, the subject does not respond but can identify the object with the left hand through touch. Here another test was done on people who had a commissurectomy. Using a similar method as the previous test, people were shown images of people. Only the image was of two separate pictures spliced down the middle. When asked to pick out the picture they had seen, they chose the face seen in the left visual field, that is, by the right hemisphere, demonstrating that the right hemisphere has a special role in recognizing faces. In this next test, people's heads were cut open and they poked at the very specific spots with an electrical charge in order to induce activation in specific parts of the brain. The people reported numbness or tingling in the skin, light flashes, or buzzing sensations. These effects are normally evoked from primary motor, somatosensory, visual, and auditory areas and pathways. These uncommon but often highly reliable phenomena include alterations to the interpretation of the patient's surroundings, such as déjà vu, fear, and dreaming states, and the reproduction of visual or auditory aspects of specific earlier experiences. That is, patients report specific memories in response to specific stimulation, and they noticed a difference between the two sides, the two cerebral hemispheres. Stimulation sites moved as far as a few millimeters over and got very different results. However, they kept poking the same spot. If they kept poking the same spot, they'd get the same results. However, when they poked that exact spot in other people, the responses varied significantly from patient to patient. It's almost like our brains are wired generally, but we each utilize them individually. This was another interesting test performed. It was done by injecting sodium amarbitol into the carotid artery. It was only anesthetizing one cerebral hemisphere at a time. In this case, the left hemisphere, which allowed the surgeon to determine whether that hemisphere was dominant for speech. The test was then conducted by asking the individual. The speech was tested by asking them to name a number of common objects presented in quick succession, to count and recite the days of the week forward and backward, and to perform simple object naming and spelling. In addition to aphasia and paresis, patients with anesthesia in either hemisphere are totally non-responsive to visual stimulation in the contralateral visual field. For example, there is no reflexive blinking or orientation towards suddenly looming objects. In other words, they did a flinch test in their visual fields, and the people didn't respond at all. The numbed side didn't respond at all. The sodium amarbitol test, like detect brain stimulation, has been very useful in determining which hemisphere controls speech. When they were doing this test, a few other studies have been done, and about 98% of right-handers and 70% of left-handers show speech disturbance after a sodium amarbitol injection into the left hemisphere. Pattern of speech representation is less predictable in left-handedness and ambidextrous subjects than in right-handers, but that the majority of left-handers do have speech representation in left hemisphere. The same study found about 2% of right-handers' speech was found in the right hemisphere, so much less significant, but still a possibility. This was an audio test that demonstrated the difference between hearing and the two halves of our brains with those individuals who had the commissurectomy. The symbol ba presented in the left ear can gain access to the left hemisphere only through the corpus callosum. If the callosum is cut, the patient can only report hearing ga. Using this task, Candace Gibson and Philip Bryden presented subjects with cutouts of irregular shapes or letters made of sandpaper, which were moved slowly across their fingertips. Their subjects showed a right-hand advantage for identifying letters and left-hand advantage for identifying other shapes. The right side of the mouth also opens more quickly and wider during the production of the syllable ma in the sequence mabapi. This test showed that there are oral asymmetries during oral and non-oral movements of the mouth. Of all the studies presented in this chapter, this one was by far my favorite. So I'll just quote it straight from the book. Perhaps the most interesting interference study known to us is an unpublished experiment by Robert Hicks and Marcel Kingsborn. They persuaded several unemployed musicians to come to their laboratory daily to play the piano. The task was to learn a different piece of music with each hand so that the two pieces could be played simultaneously. When the musicians had mastered this very difficult task, the experimenters then asked them to speak or to hum while playing. Speaking disrupted playing with the right hand, and humming disrupted playing with the left hand. So which half of our brains responds first? 6 numbers are presented for 100 milliseconds in a line going from left to right. 3 appear in each visual field such that 1, 2, and 3 fall in the left visual field and 4, 5, and 6 fall into the right visual field. Subjects were asked to repeat the numbers that they saw in sequence. As it turns out, they tend to respond with the sequence 4, 5, 6, 1, 2, 3. The subjects appear to be scanning from left to right, the contents of the right visual field followed by the contents of the left visual field. Thus, it was determined the brain has a tendency to scan information serially. In these next graphs, it shows the left hemisphere listening, and then this next one, it shows the left and right hemisphere at the same time while speaking. And you can see there's still activity on the right side, but there's significantly more on the left. And this is opposite when listening to music. I included this definition, the definition of prosody, because I had to look it up. People who are logical, analytical, and verbal are assumed to rely more on their left hemisphere to solve problems in everyday life, whereas people who are visual, intuitive, and tend to look on the big picture are assumed to rely more on their right hemisphere. So in summary, many of the functions of the cerebral hemispheres are symmetrical rather than asymmetrical. 2, the functional differences between the two hemispheres are not absolute but relative. Just because sodium amorbital renders one hemisphere aphasic does not mean that language functions are carried out only by the aphasic hemisphere. Cerebral sight is at least as important in understanding the brain function as cerebral side. Thus, the functions of the two frontal lobes, though asymmetrical, are more similar to each other than they are to those of the posterior cortex on the same side. And last, the leap from the data available to explain explanations of what those data mean is a long inferential one. Getting back to my motivation, what's my motivation to learn more? And this is all conjecture, so feel free to ignore this part. But I'll be brief. I'm LDS, and most of you probably know LDS believe in various glories to which we have the potential to be resurrected. Each one of us has a purpose and a place. To gain a place in the highest of these glories, we need to be sealed to another of our opposite sex. It's been well proven that even from birth, women are generally much better at language and could therefore generally be represented by the left hemisphere, whereas men are generally more visual and spatially oriented, which could generally be represented by the right hemisphere. So if there's symbolism to be found in this, perhaps the sealing between a man and a woman has something to do with the joining of the two cerebral hemispheres in some way at some future time. Because together our cerebral hemispheres are far more efficient and seemingly designed to be utilized in sync with one another. Chapter 12. Pages 276 to 306. People use the word sinister as a synonym for wicked or evil. Originally a Latin word meaning left hand side, our contemporary English meaning implies that left-handedness has been historically viewed at best as strange or unusual. I interviewed a father figure who said it used to be that left-handedness was even viewed by some as the sign of the devil. As ridiculous as this sounds, I think it's important to know our roots so we can correct misgivings and cultural superstitions, because there's still plenty at work in our day. Left-handedness is estimated to range from 10 to 30%. It was found that male right-handers have significantly deeper fissure on the right than on the left, but there was no difference in left-handers. How this difference between the right and left-handers might relate to handedness remains unknown. There is a larger incidence of left-handedness among mentally deficit children and children with various neurological disorders than is found in the general population. There are several theories of hand preference. The sword and shield hypothesis. The theory proposes that a soldier who held his shield in his left hand better protected his heart and improved his chances of survival. Another one is a child's world is right-handed, so in many ways, which reinforces the use of that hand. In some cultures, the left hand was considered unclean. Another is left-handedness develops through a cerebral deficit caused by accident, and there was no compelling evidence to support this theory. This image shows the similarity in brain function of twins relative to regulars like us. The blue shows dissimilarities in brain function, while the red shows similarities, with identical twins showing the highest rate of similar brain function to one another. To me, this shows just how profound an effect nature has over nurture, which begs the question, how predictive is our behavior? On the opposite side of that argument, the difference between 3-year-old and 50-year-old identical twins found a big difference in gene expression with aging. The difference was greater in twins who had lived apart and had different lifestyles, including diet and exercise. So our behavior patterns are malleable. However, it seems to take a conscious effort. There are some fairly significant differences between the cognitive function of men and women. This data shows some of the differences measured by various studies. On average, women tend to be more fluent than men in using language, and men tend to perform better than women in spatial analysis. Another big general difference is throwing and catching, visual and spatial coordination, while women's perception of language abilities surpasses that of men. These graphs show some other differences. Men are better at drawing a bicycle, women are better at word fluency. However, women and men both scored similarly in the Ray complex figure test. Men are also generally more aggressive than women. Another interesting test that showed disparity was a task to draw the water line in a series of half-filled, tilted glass jars. Women consistently underperformed on this task relative to men, and this difference is seen in both young and old subjects and in university students, whether science or non-science majors. The difference in performance is due not to the inability of women to understand the concept that the water line will always be horizontal, but rather to the fact that women are more affected by the tilt of the jar than men are. The gender differences in brain structure is another big factor here. The male brain is larger than the female brain. The differences in body size cannot account for this difference. It's about 100 grams heavier. The male brains in their sample had about 4 billion more neurons than the female brains, and body size did not account for this difference. However, the female brains appear to have larger volumes in regions associated with language functions. Women have a greater relative amount of gray matter. They also have more densely packed neurons in the Wernicke's area. While men have a larger medial frontal and cingulate region, a larger amygdala, and a larger hypothalamus. They also have a larger overall white matter volume and larger cerebral ventricles. Males have more uniform gray matter concentration. Females have more patchwork of concentration differences, as well as increased cortical thickness throughout much of the cortex. This thickness was greatest in the parietal and posterior temporal regions. The researchers also found that females have more complex pattern of gyrification in the cortex, which corresponds to differences in the underlying cytoarchitecture and increased connectivity. Compared to men, women have increased gray matter concentration in the regions of the cortex shown in color. Women have significantly higher volumes in the major frontal and medial paralimbic regions, in the purple, and than those of men, whereas men have larger relative volumes in the medial frontal cortex and angular gyrus in the pink. The purple areas correspond to regions that have high levels of estrogen receptors during development. The pink areas correspond to regions high in androgen receptors during development. This image points out that although the horizontal component was longer in the left hemisphere of both sexes, men had larger horizontal component in the left hemisphere than did women. This graph shows the weight and growth surface differences between men and women. Another interesting point was with our fingerprints, which are established early in fetal life, with the fingers on the right hand having more ridges than do fingers on the left. An interesting study found that the pattern of ridges is correlated with performance on certain cognitive tests. This was a really interesting point, that there are some differences between homosexual brains compared to heterosexual brains. Homosexual men outperformed all groups on verbal fluency, a test in which heterosexual women outperformed heterosexual men, whereas homosexual women had the lowest scores. Similarly, an examination of throwing ability showed that heterosexual men outperformed heterosexual women, whereas homosexual men threw less accurately, and homosexual women tend to throw more accurately than their heterosexual counterparts. The simplest way to relate sex orientation to brain and behavior would be the use of non-invasive imaging, although it has yet to be done to the author's knowledge. And it's interesting to note that there are measurable differences in the homosexual brain, lending direct scientific data to dispel old cultural myths that being gay was a choice. It is of my opinion that changing one's sexual orientation is akin to changing handedness. Apraxia by injury is associated with frontal damage to the left hemisphere in women, and with posterior damage in men. And aphasia develops most often when damage is done to the front of the brain in women, but to the rear of the brain in men. The number of synapses in the female rat's hippocampus goes up and down in a 4-day cycle. There is little reason to believe that similar changes are not also taking place in the human brain, albeit at a slower pace. Female rats whose ovaries are removed in middle age show a dramatic increase in dendrites and spines of cortical neurons. There's also reason to believe that testosterone affects cognition in men. The level of testosterone in men fluctuates both seasonally and daily. Testosterone levels in men are higher in the fall than in the spring, and they are higher in the morning than in the evening. Men's spatial scores fluctuate with testosterone levels. Men with lower testosterone levels have the highest scores, so there appears to be an optimal level of testosterone, and increasing the level is actually detrimental to cognitive performance. The findings then imply that maturation rate may affect the organization of cortical function, because on average girls mature faster than boys. Superior spatial abilities in boys may be directly related to their relatively slow development. Those who speak 2 or more languages are also known to have a different brain pattern, language organization, from those who speak only 1. There's even a measurable difference between cerebral lateralization in deaf people. Another study that was done after the fall of communism in Russia, many 2-year-old children were adopted into the Western world, Even with the most ideal home conditions, 10 years later, these children showed on average about 20% smaller brains on average, showing significant cognitive and other behavioral problems, showing evidence that the first few years of development have profound significance. This next graph shows that brain malleability is easier in our youth. The overlap in these triangles depicts the greater chance of hemispherical shift in specific use. So the older we get, the more specialized our hemispherical functions are. The superiority of the left hemisphere seems to be its ability to manipulate or exploit language rules, yet the right hemisphere is not without its strengths in language. Performance is better with the right hemisphere in a task that requires learning and association between nonsense words and symbols. Although the developing brain gives evidence of considerable plasticity, there is convincing evidence against equipotentiality. Animals. In animals, birds spend much of their sleep time with only one hemisphere asleep, to presumably allow them to monitor the environment for danger. This ability has also been shown in whales, seals, and dolphins, a sensible adaptation in mammals that can drown. It's also been shown that monkeys have a hand preference. In another study, it was found that Japanese macaws process communication in the left hemisphere similar to that of humans, and still we don't know why there is a difference in left or right-handedness. The only measurable thing to note is a deeper left central fissure in the right side. To close, I'd like to finish up with a few dad jokes. Dogs can't operate MRIs, but cats can. Here's a few others to enjoy. Cowboys would put a lantern on their saddle at night so they could find the trail when they were far from home. This was early satellite navigation. Thanks for making it this far into the video. We're finished. I'm out.